Everybody is talking about AI, generative AI, and large language models because generative AI is growing massively. Many people are confused and also curious to know more about generative AI. Recently, there has been a lot of changes when it comes to opportunities, when it comes to career paths, when it comes to transitioning to this particular field of data science and AI. Earlier days, companies used to ask for machine learning experience, natural language processing, or deep learning. Nowadays, companies are also asking for generative AI and large language models, implementations, fine tuning, and many more. But can we directly jump into generative AI? There are so many students that have come to me and have asked me, sir, can we directly jump into generative AI and create our career in that path? Because there are a lot of opportunities as a generative AI specialist or as a generative AI engineer. Well, the answer is unfortunately no. You cannot directly jump into generative AI without having prior knowledge on machine learning, NLP, deep learning, and various other concepts. Because if you know them, then only you can go ahead and do some R&D or some research around generative AI. Well, do you know that generative AI, large language models, the core concept is coming from the mathematics, statistics, machine learning, NLP, and majorly transformers, and of course, neural networks. But what are transformers? Many people are confused about transformers, and to be very honest, on the internet right now, there are very few videos on transformers that is giving you a concise understanding and a detailed explanation about transformers. This video is going to solve that problem. This video is an end-to-end video on transformers and the self-attention technique in transformers, because these are all the basics of generative AI. If you understand transformers, next following videos will be around various other topics that will be able to help you in your generative AI journey. Just to let you know that this particular video is a part of my data science and AI master's program that has been recently launched, doing really good. It's a 140 plus hours of program that is costed around, that is priced at around 9,999 INR, but I'm giving away it at 7,999 INR. In case you're interested to know about it, details will be in the description. Please go through it. And this video is a part of that series. So if you watch out this video, if you know, if you're able to relate, if you're able to see the way of teaching, 100% I can guarantee you that you will be able to follow rest of my videos, because I try to explain in a very layman's term. Now, the prerequisite for this video is basic understanding on NLP and machine learning. But even if you don't have that understanding, I will also request you to go through this video, understand. In case you have any questions, let me know in the comment section. Reach out to me on LinkedIn or WhatsApp if you need my help. See you in the video, and let's learn transformers.
Hi, welcome to this video on transformers. So in this video, majorly we are going to cover what are transformers and what happened in the space of machine learning, in the space of NLP, deep learning, and what were the problems that had occurred which led to transformers. Nowadays, let me tell you, all you see like ChatGPT or any kind of AI tool or generative AI tool doing machine level translational activities, doing generative AI, generating text, generating images, generating videos, each and every tool is leveraging the concept of transformers. So transformers are going to be your basic knowledge, your base knowledge before you get started with all your knowledge about the generative AI. So what are transformers? Now, traditionally speaking, I assume that you all have your basic understanding on the various deep learning concepts such as ANN, CNN, and RNN. We have also covered RNN in details where we talked about LSTMs, GRUs, bidirectional LSTMs, and so on. Right? So we all know ANN is mostly used for traditional tabular data. If you have a data set in a tabular format, ANN will be able to solve it. If you have your data set in image format or in audio format or in videos format, convolutional neural networks will be able to solve it. And when it comes to sequential data, we use RNN networks. And sequential data includes your textual data, especially in the field of NLP, right? So what are transformers? Transformers are basically neural networks. So I'm writing it as NNs. These are neural networks and their architecture is based on sequence to sequence tasks. So basically they have been created in such a way that they can solve sequence to sequence tasks with ease. That is the main concept of transformers. So there were some issues with traditional RNN models which they were not able to solve. Obviously, we will be talking about those problems in the coming minutes. There were certain amount of problems which transformers is eventually solving them. And let me also tell you, when transform the official paper of transformer was launched, I think it was introduced around 2017. Now when it was launched by Google Brain. The paper was launched by Google Brain, and it was around, I could be minutely wrong. I'm not sure whether it is 2017 or 16, but yeah, I can check it out. You can also Google it out. Google Brain Transformers paper. If you search on Google, you will get it. Around 2017, they released a paper, and that paper was basically a revolutionary paper, which means they even didn't knew, the Google Brain people, the researchers even didn't knew what transformers will be doing in 2024. And we all know what's happening in the world right now. People are going crazy for chat gpts, people are going crazy for various AI tools. Billions and billions of investment is happening around the space of AI, right? Now even we are in a situation where people are confused and also scared what will happen to their jobs. However, let me tell you, there is no problem with respect to AI engineering jobs. Nobody can replace us, at least for the next 5 to 10 years, so don't worry about it. So coming back to this topic of transformers, as I told you, transformers are neural network architecture for sequence to sequence tasks, which basically means your input is also a sequence and your output is also a sequence. Now, what are the examples of this? Now, the examples of this are many. You can talk about machine translation. You can talk about question and answer systems, chatbots, text summarization, and many more. Okay, so basically you have sequences in your input and you are having sequences in your output, sequence of sentences, right? Now on the left hand of the screen you can see a beautiful architecture which looks little bit difficult to understand and grasp, but do not worry, we'll cover that. So this part is basically your encoder and this part is basically your decoder. Okay, so I'm expecting you all know the concepts of encoder and decoder, right? Now apart from that, you can see the input embeddings, the output embeddings, and so on, right? Now to summarize, transformer architecture is nothing but a neural networks architecture. It is based on the principles of sequence to sequence. It is also an encoder decoder concept. And special thing, let me write it down here. First of all, it is a neural network architecture. Second of all, it is a sequence to sequence architecture. Third is encoder decoder concept. Encoder decoder concept. And the fourth is the most important point, which we will have a separate video, which is called as self attention. Now this is based on the principles of attention. Okay, what is attention? We will be explaining you that. Now let me jump back to the historical part. As I told you, there was a paper that was launched or introduced in 2017 by Google Brains. Okay, you can Google it out, you will find it. So after this there was a revolution, and now we all know how famous transformers are and transformer based models are, right? ChatGPT is nothing but a transformer. Many of you have been using ChatGPT might not know what's behind the hoods. It is nothing but a transformer. Okay, so it's a revolution. Now, what is the impact of transformers? Let me also show you that. The impact of, let me use this, impact of transformers. Now, there are multiple impacts of transformers. Okay, so let's say I'll talk about the first impact. The first impact is the NLP revolutionizing. That means there were some traditional issues with NLP which are currently being resolved by transformers. So in the space of NLP, if you talk about the research, first came the heuristic approaches, right? All the heuristic approaches. Then came all the various machine learning statistical concepts of solving problem. Then come your RNNs. Then comes your LSTMs to solve some of the problems that we're having with RNNs. And finally, there are still some problems with LSTMs where transformers came into picture. Okay. Now, the great example is ChatGPT, right? The second impact of transformers is democratizing AI. Democratizing AI. Now, what do you mean by that? Now, using pre-trained models, you can actually build a lot of AI tools. So there are already a lot of pre-trained models of transformers available on Hugging Face and various other platforms. You can leverage those and you can build a lot of AI products. Right now, if you see any product, anything, like you pick any use case, generation of images, generation of text, automated resume parsing, some tools for giving you AI, resume based AI services, um, insurance AI claims, AI based claims, AI based bots, AI based girlfriends, AI based boyfriends, whatnot. A lot of things are happening in this space, and that is because of leveraging all the pre-trained models by the transformers. The third is multimodal capabilities. Multimodal capabilities. Okay, now what do you mean by that? So it means it basically works with any kind of data. Okay, so apart from textual data, you also can work on voice, you can also work on videos, you can also work on various other things. So it's not just only with texts, you can work with a lot of things, and that's where generative AI comes into picture. And generative AI is not about text. People have a confusion, generative AI is textual related. No, textual related is large language models where you only deal with textual data. We have generation of images, DAL-E. We have generation of videos. Now we have Sora. So it has multimodal capabilities. Then comes the acceleration of Gen AI. As I told you, because of transformers, this concept came into picture, generative AI. And lastly, we have the unification of deep learning. Unification of deep learning, which means, try to understand, it's a very important concept. Before transformers, before all these generative AI concepts, we only had some neural networks, right? ANN to solve tabular data, CNN to solve images data or voice data, RNN to solve some textual data. Now we have transformers to solve any kind of data. That is the unification of deep learning. So with the power of transformers, you can actually do a lot of things, right? It's fascinating. It's a very important topic. There are some complexities to understand the architecture, but I will try to make sure that your understanding is easier. So let me get started with one of the previous papers that came in 2014. So there was a paper, something like sequence to sequence neural networks, and this was by Ilya I forgot the name. Wait 1 second. Sequence to sequence 2014 paper. Yeah, 𝐓𝐢𝐦𝐞𝐲𝐞. If you just search this thing, sequence to sequence neural networks, or just search sequence to sequence learning with neural networks paper 2014, you will get some 𝐓𝐢𝐦𝐞𝐋𝐢𝐬.org platform. I can also give you the link of this one in this video. You can probably type in yourself. Let me just copy paste this. So this is the link. Okay, it's not that difficult link, so just type it out and you will be redirected to this particular page. In case by the time you are watching this video this paper is not available, as I told you, just google it out, you will be able to understand. Okay, now sequence to sequence neural networks was introduced in 2014. There was a paper by Ilya. Basically it was to solve sequence to sequence problems using the encoder decoder technique. Okay, now if you talk about the architecture, this is how the architecture looks like. So let me draw, and then here we have an embedding. Here we have another embedding. And then let's say your input goes here. Okay, obviously input goes from here also. Okay, now let's say my input is very simple. My name is Satyajit. Okay, now we have LSTM here, we have LSTM here, we have LSTM here, we have LSTM here, and this is basically passing the data, and eventually this passes the data to the decoder. So we have HT and CT. Now this is your encoder, this is your decoder, right? Inside your decoder also you have some cells which passes the data, and you finally have your output here. Okay, so you can have a softmax layer, and then you can have the final output. So something like this was the architecture. Okay, now try to understand this architecture. It is very simple to understand. The left side is your encoder, your right side is your decoder. Okay, now basically data goes from here like this. Okay, now what happens here is, so this is a step by step input, right? That means first goes my the word my, second goes the word name, third goes is, fourth goes Satyajit, and eventually all your data is in your encoder. Then you are passing the data to the decoder, right? So basically encoder processes and maintains the hidden state and process the full sentence and creates a context vector which is CT, right? So the entire text as a sentence is read, then only we are generating CT, and then we are passing it to the decoder, right? That is the thing. Now decoder again basically goes through step by step process to eventually do the final output. Now try to understand this thing. This particular architecture works really good for smaller sentences. Let's say my name is Satyajit. If you want to do a translation, yeah, it will work because it understands this is one sentence, it understands this is an entity, how to process the data, how to translate, it will be able to perform well. But for larger data, if the corpus is huge, the input is huge, it will not be able to solve this problem because it is taking everything and then processing it and then sending it to the decoder. So it will not work. Now the problem of this, and this was in 2014, so you can remember, you can understand that from here till 2017 lot of things happened incrementally, and finally in 2017 we got this paper on paper by Google Brains on transformers, which is actually solving all this problem. Using transformers you can train like millions and terabytes and gigabytes and petabytes, whatever bytes you can call, those kind of data, and that's how we have ChatGPT, right? So in 2014 this was a very initial idea. very good architecture, but it had flaws on larger data. And then comes another paper. I forgot the year that was in which year this paper was live. I don't remember, but you can just Google it out. The paper name is Neural Machine Translation by Jointly Learning to Align and Translate. Now, this was by uh, Dmitry, sorry, Dmitry or Dimitri. Just one second, let me search. Yeah, Dimitri Bahdanau. Okay, if you search, you will be able to get it. So again, this paper solved some of these flaws, but it was not the best. So, anyways, let's talk about this paper. Now, this paper was basically in which attention concept was used. This is the first paper which basically talked about attention concept, which we know right now is one of the most important thing in transformers. In transformers, without attention, you will not be able to solve any problem. Attention is the main focus in transformers, which was touched in this paper. Now, what do you mean by attention? So try to understand again this thing. So let's say I have an architecture and I have some hidden cells. So we have input when we are passing. Let's say this is my input. Turn off the lights. Now this is your H1, this is your H2, this is your H3, this is your H4, and finally you have. So this paper basically focused on one concept, which is attention. What this paper told was, do we actually need the entire sentence? Let's say we are, okay, I did not talk about the problem statement. The problem statement here is, let's say I want to translate English to Hindi, or maybe English to any of your local languages that you are familiar with. I'm just giving an example with respect to Hindi. And you can see this paper was all about machine translation, right? It was using the concepts of sequence to sequence, and it is solving some of the sequence to sequence problems with respect to machine translation. So basically this paper talked about a concept that while we are solving this problem of converting English to Hindi, now if I convert this into Hindi, what will be the Hindi? Turn off the lights. Again, I'm not great with Hindi. However, Hindi was my major during my school days, but I might be grammatically wrong. E and badi, choti, I could make a mistake, but I think you are understanding, right? Or if in your Odia, let's say I'm basically coming from Odisha. Let's say I'm converting this data into Odia. So light bond karo, something similar. So, or else if you want to convert it into any other language. So the core concept here is, let's say we are translating this to this. Do we actually need the entire sentence? Now, for example, turn off basically means band, right? Turn off means band. So to have band, if you have two inputs, let's say x1 and x2, I think you are solving the problem. To find light, you just need x4. You don't need x1, x2, x3 and x4, right? So the main concept that was uh, you know talked about in this paper was, instead of sending the full input context vector, that the way we were sending here, we were parsing the entire data and then sending the context vector. This paper basically talked about, instead of sending the full input context vector, um, can we just send some of the inputs and still get things sorted out at the decoder level. Can decoder understand? Yes, decoder can understand, right? So let's say from here, let me try to draw this thing. Okay, I'll okay, let me draw this thing. So let's say you have this. I'm drawing the decoder. Okay, so basically understand, so encoder and decoder are connected, right? So let's say here comes my first, second, third and fourth, and let's say we have 1, 2, 3 and 4. So here I am predicting light, here I am predicting band, here I am predicting karo, and here there is a end of sentence. Here it is the beginning of sentence. So here is where, so basically this line is coming here. Sorry, let me draw it properly. So what's happening is this line is basically coming here and it is being fed here. Okay, and what's happening is, now this is a traditional encoder decoder technique that I'm talking about, right? So here what's happening is, this is your starting and this is your light, this is your band, this is your karo, right? So the concept was, can we use only certain inputs to kind of generate the decoder outputs? Yes, we can. And that's where the concept of this architecture came into picture. So this architecture is something like this. So you have your input, or maybe you can consider it as your encoder, this is your decoder, and these are your 4 inputs, right? This is your turn of the lights, and here we have light, band, karo, okay, and then end. So what's happening is, so let's say, just give me 1 second. So this basically tells you that here you have your inputs, right? You have the start, here you have light, here you have band, and here you have karo. So what it is telling is, instead of the traditional approach where we were directly passing this, sorry, maybe we'll do it here. Instead of the traditional approach, which is something like this, we have encoder and decoder, we were doing something like this, right? In the very first approach, if you remember, same, right? Encoder, decoder and something like this, right? So you are passing the HT and you are passing the CT as well, right? In this particular approach, what it is telling is, individually you will be passing the context. You do not have the context of the entire sentence, however individually you are passing this context. So I'm just rejecting this one. Okay, this is just for demonstration. This line does not exist, right? Now C1, C2, C3, C4, maybe C1 depends on let's say H1 and H2, let's say C2 is only dependent on H3 and H4, let's say, right? So you basically do not need the full input sentences to solve this particular problem. Now here the formula is very simple. Ci at any input in your decoder is summarized as Li JHI, which basically means this is your attention weights. Okay, so attention is something like, if you are trying to predict light, that means this H4 is very very important to you, because your mind is focused on this word. When you're translating this in your head, turn off the lights, okay, lights band karo, lights, when you're targeting first output, lights band karo, okay, lights is basically coming from my 4th word. So think from a human brain point of view. When you're trying to translate from the Hindi perspective, the output of Hindi perspective, each word is actually dependent on a specific input, right? So that is your attention layer. So to predict CI at any point, This is the formula, summation of 𝐓𝐢𝐬𝐻𝐈. Okay. Now in this technique, translation quality increased. After this paper was released, translational quality increased. But there was still some problems. Attention based encoder decoder still had issues in sequential learning, which basically means when you are transferring the input through sequential data and when you are dealing with huge data set, it is still slower. So in large data set, we cannot perform. Forget about fine tuning. Now, fine tuning and pre-tuning is completely a different topic. It is very, very difficult to process larger data. Okay. Now also try to understand this concept. Let's say I'll randomly take something from the internet. Just give me 1 second. Let's say okay, let's say I got some input from the internet. Maybe I'll be using that here as a text. Okay, now I just got a text, a paragraph from our captain of the Indian team, based on our captain of our Indian team, like who led to our 2011 victory. I think every Indian should know about him. But anyways, that's not the focus. The focus here is the entire paragraph. Try to understand this thing. Now, if I ask you to pause this video and try to create the translation in your head in your local language, is this possible? I mean, from a human point of view, it is still difficult, right? When you are processing Mahendra Singh Dhoni, commonly known as MS Dhoni. Okay, so Mahendra Singh Dhoni, जो MS धोनी के नाम से भी जाने जाते हैं, is an Indian cricketer who is widely regarded. Okay, एक भारतीय क्रिकेटर है जो one of the greatest. So what's happening? What's happening in your brain is you are not able to process the entire thing. If I ask you, you have to process everything at one go and then give a translation. Not possible. Even human brains will fail. Human brains will also fail, right? So what is the solution? The solution here is breaking down the text to chunks. Okay, so anyways, jumping into our last paper, so this was one of the problems. Jumping into our last paper, that is where everything started in 2017. The paper's name was Attention is All You Need. Attention is All You Need. And that was a very catchy title, right? We all need attention in our day-to-day life also, apart from studying, apart from neural networks. In our family, we need attention from our wives, from our girlfriend, from our kids, from our parents. Everybody needs attention, right? So it is a very important topic that was tossed by Google Brains. Now try to also understand that whenever researchers works on research papers, they basically work on incremental strategy. That means somebody wrote a paper, then we revolutionized to another topic, then we are revolutionizing to another topic, right? This is the usual flow. But this paper did not take any inputs from the previous paper. In fact, this paper was something basically like a time travel. Like it was written in such a way that somebody from the future 2025 or 2030 basically came to those researchers ears, told that this is what we need to do in 2025, 2020, 2030, and they wrote it. I mean, it is amazing, and all the advancements that's happening is based on this paper. And this is where your architecture comes into picture, which is your transformer architecture. I will take this into on the screen so that it is visible to you. Now this is where the concept of self attention comes. That means your brain when you are processing large data, you are basically processing chunk by chunk, right? महेंद्र सिंह धोनी, commonly known as MS धोनी, okay, महेंद्र सिंह धोनी जिसको MS धोनी के नाम से जाना जाता है, is an Indian cricketer, एक भारतीय क्रिकेटर है, who is widely regarded. So you're taking English sentences chunk by chunk by chunk, and you are feeding it to your memory, and your memory, when you're feeding it, that is the self attention you are trying to give to your brains, and that is available in this beautiful architecture. So let's try to talk about the beautiful architecture and what are the features of this transformers, and in the next video we shall be talking about the self attention mechanism. So this has a better architecture, sorry, so this has a better architecture, stable architecture, I would say, stable architecture, very robust and revolutionizing. And these 4 points are not enough. I mean, whatever you say, how much you want to praise, it is less, because this is a revolutionizing thing that the world is seeing, right? So we will be talking about this architecture in details for anyways, but this is just an overall idea about transformers. In the next video we shall be jumping into the self attention technique. Hi, so let's talk about our next topic, which is self attention. In the previous video I touched this topic of self attention, right? Now we will be talking about this in depth, because this is one of the most important topic when it comes to transformers. It is the core concept basically. Now first let's talk about some NLP applications. In NLP applications, what are we solving? What is the most important requirement? What is the most important requirement in an NLP problem? Can you please pause this video and try to answer this? So I know the answer that you might be thinking is, see, there are different answers that you might be thinking. The most important requirement could be data. The most important requirement could be something else. The most important requirement could be the conversions of words to text, or the most important could be intent identification, right? But I would say this is, sorry, words to text, my bad, words to vectors, right? Words to vectors. So in my knowledge, this is by far one of the most important requirement, right? Most important problem. Now why it is the most important problem or the most important requirement? Because ultimately you will be passing your data to computers, right? And computers only process numbers, right? They only know numbers. So you need to convert your words to vectors or numbers and then pass it to your computer model, right? So in the past we have seen how NLP has evolved, starting with some of the basic techniques. Let's say one hot encoding. Let's say we talk about cat, rat and mat. Let's say 100 010 001. So cat can be represented as 100, rat can be represented as this, and mat can be represented as this, right? Similarly, moving ahead, we also had some techniques like bag of words, right? Let's say I love, sorry, my bad, I love cats, cats love humans. So how many words? I love cats, humans. So 1 2 2 1, right? This is how your bag of words technique works, right? And similarly we had lot of other techniques, but there was a revolutionizing concept called as word embeddings, right? If you remember word embeddings, that was taught in NLP. Now word embeddings were able to solve some of the problems that the initial issues had, right? Because it was based on the semantic meaning. Now try to also understand this thing. Let's say you're training a large corpus of data, right? You feed it to your neural networks. Basically, they usually understand the words, right? Understand the words. And that is how the advanced word embedding techniques work. They understand the words and convert it into a n-dimensional vectors, right? If you remember, we talked about all these concepts in NLP, right? So if you remember CBOW or skipgrams or glove, or not glove, or fast text, we know that if you have a large corpus of data, you can convert it into a 300 dimensional vector. If you remember fast text, right, we were able to convert it into a 300 dimensional vectors. So I'm talking about that particular concept. So you have a large corpus of data, you feed it to your neural networks, understand the words, and convert it into a n dimensional data. Now imagine in this particular scenario, I'm talking about a 5-dimensional data. Okay, so let's say we have king, which is, let's say, 0.7, 0.1, 0.1, 0.9, 0.4, 0.3, right? And we have queen, let's say we have 0.6, 0.1, 0.9, 0.1, 0.9, something like that. Now here imagine your first concept, first vector dimension is basically your, let's say, how rich they are, maybe, right? When king and queen are usually rich, that's why you see a higher number, right? Now if you try to visualize this into a two-dimensional graph, because I cannot visualize it on a five-dimensional graph, so on two dimension you can see the king and the queen vector is somewhat similar based on the cosine similarity concept, right? Here comes the concept of cos theta, right? And let's say you have another keyword, let's say happy or something else, let's say cricket. So cricket could be somewhere here, right? It is completely different from other words. Now try to understand the concept of attention. So I was just talking about the revolutionization of NLP, on how we moved on from different concepts, and now we are going to enter the era of transformers, which is basically solving the problem of attention. Now what do you mean by attention? Before that, let me try to draw a simple diagram. So we have, let's say, an encoder and we have a decoder. Okay, so here let's say we have some neurons and here we have some neurons. Okay, now let's say what goes here is a simple line. Let's say we will take the same line that we considered in the last session: turn off the lights. Okay, now internally this thing happens and you have this, right? And let's say here you have light, band, karo, and here you have the end. Okay, now this, so let me draw the full box around it. So this is the full box around it, right? Now try to understand, this is your decoder and this is your encoder, right? Now encoder basically creates a summary of the entire text, right? So the first step is encoder creates a summary. So the entire text summary it creates, and then it converts it into, let me not use numbers, I'll directly do arrow based architecture or flow chart. So we have encoder that creates a sentence, creates a summary, then basically it converts it into vector. Agree with me? Yes. Now as input passes to the decoder, let's say you pass the vector information to the decoder. Decoder basically works on a step by step approach. right? You can see step by step approach, and then it basically predicts light, whatever it is, light, band, karo. So step by step it is predicting. You can see the first output is light, then band, then karo. Now why do we need attention? Try to understand this thing. Now when you're talking about huge corpus, let's say in the previous example I was talking about a huge corpus about MS Dhoni, right? Let me just quickly get exactly the same thing, or maybe a different text about Dhoni. Just 1 second. Let me use Wikipedia and get those text, and we will be using that for our example. So let's say I want to take this entire sentence, and I will decrease the font so that it fits to our screen and we will be able to understand. So try to understand this concept. Now here what's happening is you are having this big input, right? Now again the same activity, try to pause the video and take as much time as you want and try to translate it in your head without using Google Translate or without using any kind of translational tool. Now if you start doing so, it could be a nightmare for you to translate this thing. Even though you will be able to understand, your brain will be able to understand each and everything, but translation will be difficult. Let's try that. Let's try to pause this video and try it out. Now when you try doing this translation thing, right, what your brain processes is line by line, right? MS Dhoni, also known as Mahendra Singh Dhoni, is one of the India's most iconic and successful cricketers, born on July. So here our brain takes a pause. Okay, MS Dhoni. So MS Dhoni जो महेंद्र सिंह धोनी के नाम से भी जाने जाते हैं, भारत के बहुत ही सक्सेसफुल, आई डोंट नो सक्सेसफुल का हिंदी क्या है, प्रसिद्ध, भारत के बहुत ही प्रसिद्ध क्रिकेटर हैं, right? So what's happening is you are taking chunk by chunk, feeding it to your neural networks, your brain is processing it slowly, right? Just think this way, if your brain, which is a super powerful neural networks, is facing this problem, why can't a simple encoder decoder technique will not have a problem? So this was the problem statement with any kind of encoder decoder technique. When it comes to big sentences, when you are trying to summarize it and pass it to the decoder, there are some techniques like focus words. You cannot have focus words while you are transferring the data from encoder to decoder, because you are transferring the entire corpus or the entire paragraph, right? So if human have challenges, how machines will work? Now the concept of the previous paper that we talked about, that paper on the machine translation, right? For prediction of this, do we actually need the entire input? The question is valid, right? Because we logically need only this for prediction of light. We only need lights. If we are able to create a model, something like this, which can understand for each and every prediction which input from encoder it is using, then our life is sorted, right? And that is the problem we are solving using transformers. For band, what do we need? We need turn off. So we need basically H1 and H2. For light we need H4. We don't need the entire corpus. So the solution was very simple. Human being which were not able to translate the whole paragraph, we usually do it chunk by chunk, right? We also have an attention mechanism on important words. So in this case, in decoder t equals to 1, so this is your decoder t equals to 1, right? Here what's happening is we only need the encoder t equals to 4 and so on, right? So Let me redraw the structure. I think we can use the same structure. So that is where the concept of transformer came. Okay, I will redraw this structure. Okay, we can reuse it actually. We can reuse it. So let me just copy paste this. It's okay. We will create new. Okay, because we need to create fresh so that it looks clear, because there are so many arrows and all, it will make you confused. So we have this encoder, we have this decoder, we have all this. Let me draw and then I will explain. So this is a connection, and here comes your input, and let's say here you have H1, and we have outputs here. Okay, so let me draw it in a different color. So we have light, band, curve, and this is end, right? And here as an input comes starting, and this is light, this is band, this is curve. And similarly in your input, turn off the lights. Now try to understand this thing, that these are nothing but your H1, H2, H3 and H4, and these are nothing but your S1, S2, S3 and S4. Okay, now instead of the traditional approach, we are introducing C1, which is your attention unit, C1, C2, C3, C4. Okay, so these are your attention units. Now at time step 2 in your output layer, I'm talking about time step 2 in the output layer, what all inputs do you need? So let's say you need, time step 2 is this. Okay, what inputs do you need? You need S1, this thing you need, yes. What else do you need? You need, so this is your Y, let's say this is your Y0, this is your Y1, this is your Y2 and this is your Y3. So this you need, right? Y1 you need and S1 you need, right? Now this is the traditional thing, right? In your decoder layer you need two inputs, which is this and this. Now I'm just talking about the traditional encoder decoder technique, right? You are processing the entire input, which is turn off the lights. From your encoder you are passing it to your decoder, right? And in your decoder at time step 2 you only need S1, that is coming from the previous unit, which is from this block, and you need this Y1, right, which is light. So for now, to predict, you need this and you need this. To predict what? To predict band. And there is a problem, because you are taking the entire text or entire input sentence from the encoder to decoder. Now the question that was coming is, do we actually need the entire text, the entire corpus? We talked about the problem, right? The problem is this: neural networks will not be able to process large amount of data, so we need attention. So here the problem changed from this, and now using transformers at t is equals to 2, if you want to expect an output called as band, you basically need y1, s1, and on top of that you also need, let me draw the bracket, you also need something from the encoder. What do you need? You need basically, let's say, H4, or maybe combination of combination of H. Okay, let's say for light you need combination of H, right? You need H4. For band you need combination of H1 and H2. I'm just giving an example. So H1 and H2, that is what you need, right? And that's where this concept of C1, C2, C3, C4 comes in. C1, C2, C3, C4 are nothing but your attention units, or you can call it as attention weights. Now in your vanilla encoder decoder technique, at time is equals to I, what happens is you basically take y of I minus 1 and s of I minus 1. And in this, now in this architecture, at time is equals to I, you are basically taking I of y minus 1, y of I minus 1, s of I minus 1 and c of I, and this is nothing but your attention input. Okay, now what is Ci? Just think about it. What is Ci? Ci is a vector, scalar or a matrix. So think about it. What is Ci? Because Ci is nothing but coming from multiple hidden states of your encoder, right? What is the purpose of Ci? The purpose of Ci is to identify at decoder t equals to I. Which Ci is important? What is the dimension? So try to understand the dimension of Ci is exactly same like Hi. If Hi is 3 dimensions, Ci is also 3 dimensions. If Hi is 4 dimensions, Ci is 4 dimensions. Okay, so I hope this is clear, right? Now I will move on to little bit more complexity. So the formula at Ci is nothing but denoted as alpha 1 H1 plus alpha 2 H2 plus alpha 3 H3 plus alpha 4 H4. Now what is alpha? Alpha is nothing but the inputs from these are alpha 1, alpha 2, alpha 3, alpha 4. Similarly, we also have multiple alphas here. Now if you want to draw this, just take it down and try to redraw this because it is already complex. So try to understand. Alpha is the connection from your encoder to the decoder layer. So let me draw using black lines. Okay, so let's say black line is even confusing. Okay, similarly for second one you also have this, right? Similarly for third one you have this, for fourth one you have this. That means all of these are connected, right? So to reduce the confusion, instead of this complex thing which will eventually have how many alphas? Alphas will be 4 cross 4, right? Because 4 in the input or in the decoder and 4 in the encoder, so it will become 16 alphas, right? So let me undo it so that we will reduce the number of alpha lines and to reduce the confusion. So how many alphas do we have? 4 in the encoder and 4 in the decoder, so total 16 alphas, right? I'm just talking about this one, alpha 1, alpha 2, alpha 3, alpha 4, and that is what it is. C1 is nothing but alpha 1 of H1, alpha 2 of H2, alpha 3 of H3 and alpha 4 of H4. Simple, right? Similarly for C2, let's say if you want to generalize it, you can call it as alpha 1 1, alpha 1 2, alpha 1 3, alpha 1 4. So C2 becomes alpha 2 1 H1, alpha 2 2 H2, alpha 2 3 H3, alpha 2 4 H4. I hope you are able to get right. There are 16 alphas, alpha 1 1 to alpha 1 4 for my first encoder to all the decoders, alpha 2 1 to alpha 2 4 from my second encoder to all the decoders, alpha 3 1 to alpha 3 4, alpha 4 1 to alpha 4 4, right? That is what it is. So the generalized formula is my C of I is nothing but summation of alpha ij h of j. Now consider encoder has j units and decoder has I units. Alpha, how many alpha we will have? I cross j, right? In this case, luckily I and j is same. That's why it is 4 cross 4, right? So this is the generalized formula. Okay. Now let's say you are considering alpha 21. What is alpha 21? Alpha 21 is basically here with respect to this one, right? So for band, so alpha 21, wait. Yeah, basically, yeah, I also got confused. So alpha 21's output is band, right? For alpha, so for this particular cell in your decoder, what is your input in the decoder? The input is this, right? Alpha 21 is basically what is coming from this keyword called as turn, right? That is what we need to understand. What is the important, what is the role, right? And that is all about your attention. Let's say you talk about alpha 21. Alpha 21 is nothing but combination of H1 plus S1, right? What is S1? S1 is this thing. And what is H1? H1 is this part, right? So try to understand. This can also be written as this is a combination of H1 and S1, it can also be written as function of H1 and S1. Now what do you mean by function in neural networks? Your function could be anything. A very simple function is nothing but a ANN architecture or a ANN model, right? So what is ANN? We all know we have inputs, we have some hidden layers, and we have output, right? So what's happening here is we have bunch of neurons. So let's say I'm just using a magnifying glass and I'm just trying to expand this. So what happens is you have a neural network. What is going as an input is from the decoder we have the S1, from the encoder we have the H1, and the output is nothing but alpha 21. Now I think you will be able to understand what is alpha 21, right? Alpha 21, I will repeat, is for my second object in decoder, which is my this block, I'm talking about this part only. That is my alpha 21, right? So how does my alpha 21 gets calculated? It is calculated on based on this. The input of S1, which is this, right? This, and the output here, this, they are combined, goes through a ANN architecture, and then alpha 21 is calculated. And we all know ANN is nothing but a beautiful neural networks which has a concept of backpropagation, and we can adjust this, right? That is basically the attention we are talking about mathematically.
So that's all about transformers and the self-attention technique in transformers. I know there were prerequisites of some neural network techniques or some NLP techniques in order to understand transformers, but trust me, yes, we are studying transformers. There are some pre and there are some post videos that will basically help you to get more understanding on transformers. If you are a part of the data science and AI masters program, definitely you will be able to relate what I'm talking about. In case you're interested in my program, let me know, or else reach out to me on WhatsApp and we can discuss. We can check your resume, we can check your background, and then only I can guide you whether this is the right program for you or not. In case you have any other questions, let me know. That's all about it. See you in the next video.